Hello, welcome. Let's get started. This is going on YouTube. In case you missed the stream, the whole point is, to teach people some concepts on computer science. Hopefully, you'll learn how to program. You'll get good content from what it would otherwise be like a computer science class in a prestigious university. And so I am following a curriculum of some online courses on some Ivy League universities. Let's just put it that way. And I am distilling about 2 1-hour classes for 1 hour of basically my stream, which I think is pretty good. So you're getting a condensed version of what you would get in a computer science class from Ivy League schools. Today we're gonna go over. I'm gonna bombard you with some theory, some concepts. So bear with me on that. I think they're important. Again, I'm following the curriculum of computer science course in a Ivy League school, so this is kind of like what you would see there as well. And so we're going to do a little bit of programming, but most of it is going to be theory. So again, this is going on YouTube for you to watch it and rewatch it as you try to learn these concepts. All right. So last time I owed you, we're seeing the first computer bug, and it was actually like a piece of paper with like a moth taped onto it. The person that reported that bug was Grace Hopper, Dr. Grace Hopper. You can see her picture here. I owed you her name last time. Pioneer of computer programming, invented one of the first linkers, and we're gonna see in this stream what a linker is. But the word bug didn't start with just that moth per se, right? That was just kind of a coincidence. Thomas Edison reported bugs in his designs as early as the 1800s. Also, the computer that Grace Hopper was working on, that I said that they crawled in and found the moth, that was the Mark II at Harvard University around 1947. Right? So that's some information that I owed you last time. And with that, again, history of computing. This is important. So my goal is to teach you a formal computer science course. The benefits are like, number one, you don't have to pay for it. It would be pretty expensive, especially in one of these Ivy League schools, right? And number two, because it's important for people to have the context, right? You might think, well, I just want to learn how to program, but like theory gives you some context, right? And history of computing gives you some context. And one of the things that I feel sad about these days is that a lot of programmers, and I mean a lot, maybe the majority, don't have that context. And it's not that I expect everyone to have a formal computer science degree, but I think this is important. Let's just put it that way. All right, so very quickly, first computing device, the abacus, about 4,000 years ago, really. That's when, computer doesn't mean, oh, it's like a laptop or a desktop that we, nowadays think of. Really, computing, the word computing we've been computing for, long time. In the 1800s, Charles Babbage was a Lucasian chair in Cambridge, England. He designed the difference engine and analytical engine. And this was a computer that started not as a physical thing, but as like a theory thing. And there's actually a branch of computer science that's automata, I want to say. Yeah, theory of automata. And it's just like, you draw on piece of paper these theories basically, and you don't need a physical computer, right? It's all mathematical almost. It almost feels mathematical. And so that's what Charles Babbage kind of designed, if you will, this difference engine and analytical engine. It was more theory based and mathematical based, right? And so related to that, the first programmer was Ada Byron, which devised various programs for Charles' numerical engine. And again, this wasn't like a physical machine, it was just a theoretical machine, more or less. Right? In the 1930s and 40s, the first prototype of electromechanical computers, and the word mechanical is, you have to imagine it wasn't just electronical. And then on the 1946, we saw the first, basically the first modern computer, if you can call it that, right? And it was called the ENIAC, Electronic Numerical Integrator and Computer, right? And it was, kind of like the name says it was more for mathematical calculation, so to speak. And then we go all the way to 1971 and we see the first microprocessors, and that kind of got us started with what we know today as computers and smartphones and tablets and all that good stuff, right? So this stuff is important, but I mean, we're not gonna see it ad nauseum. We're just, it's just here because it's important. It's part of a formal computer science degree, and it doesn't take that long. Okay. All right. Just to be clear, definition of computer science: study of problem solving with computers. Right. Basically, that's it. Right. It's called science for a reason, but I want you to pay attention to the word or the words problem solving here, because that's the way I look at it. Right. And computers, a computer program is more or less like a puzzle that you need to solve, right? You have a problem and you need to think about, how am I going to solve that problem, right? That's what this is about. It's not about writing code. The writing the code comes after you start thinking, what do I need to do to solve this problem, right? And so it's not only what do I need to do, it's like, what do I need to do so that the computer understands me when I tell it what I want it to do, right? And so with that, I have an interesting thing in here that we were doing last time. Remember the little Minecraft that we were doing last time in code.org? So I was doing this. This is like section 7, and what you need to do in here, remember this is kind of like the code that we need to put in here. It says it's good to plan ahead, plant crops on both sides of the water so you don't get hungry later on, right? So you got to stop and think about it for a minute. And I found myself rushing through it and making mistakes. In other words, making bugs in the code. Right? But the point I'm trying to make in here is like, this is almost like a puzzle, right? What do I need to do? I need to plant crops on this side, and then I kind of like need to walk over to the other side and then plant crops on this side, right? So let's just try it together. So what do I need to do? So I'm on the dirt, so I probably, and I need to do it several times, so I have a repeat loop. Remember last time we saw 4 loops? 1, 2, 3, 4, 5, 6. So the 6 is fine. I don't need to change the 6. And I want to plant crop, right? Let's just run that. All right. So obviously that was wrong. You see, and this is what I'm saying. If you kind of rush through it and don't think about it hard, you need to reset the program and try it over, right? But no matter how good of a thinker you are or how good of a puzzle solver, more likely than not, you will find yourself, trying something out and then running it, and then it doesn't work, and then you change the program and you run it again, and it doesn't work, and then you run it again, and so on and so forth, right? And so that's a process of debugging, right? We call that debugging. And you just saw, like, I tried to rush through it, and I thought it was going to plant the crop 6 times, but it didn't plant the crop 6 times, right? Or maybe it did, but it planted the crop on the same spot. So now what I need to do is, after planting the crop, I need to move forward, right? Let's try that. Let's reset it and run it again. All right, now it's kind of doing this the right thing, right? Okay. All right. So it did that part right? So now I need to turn right, I think. Turn right, and then like move forward 2 steps, right? And maybe do another repeat 6 times, right? And then plant crops, and then move forward again 6 times, right? And let's see what that does. Run again. Whoops, what happened? Oh, okay. So I did this inside the loop, right? So I planted 1 crop, move forward 1 space, we turn right and then move forward, and we're in the water, right? So again, you know, this is about debugging, right? Seeing where you did things wrong. So the move forward actually comes after the loop, right? So I move forward and then I move forward, and then I can repeat and plant my crops again, right? And then the turn right, it's also after the loop. All right, let's reset it and run again. All right, so now it's doing. Yep, another bug, right? Did you see that? It went this way instead of moving right, and it's planting crops now on this spot, right? So what did I do wrong, right? So it planted all these 6 crops, great, right? And then we turn right, we move two steps, but I forgot to turn right again. You see? So I forgot to turn right again down here, right? And if I turn right again, now I can plant another 6 crops. Okay, let's try that. Oh, okay. So what happened? I'm missing 1. 1, 2, 3, 4, 5. Why didn't I plant 6 crops? Oh, okay. I know what happened, right? I planted a crop here, right? And this is important because we're going to see this. This is what is called an OBOB. And to be honest with you, I hadn't heard that term until I attended one of these Ivy League classes. And an OBOB is off by 1 bug. OBOB, right? So I'm off by 1 in here, right? I didn't plant a crop here, but I think what happened is I planted this 6 crops over here, right? And then I turn right over here. I advance 2 steps. I turn right again, right? But then I didn't move forward. So I started planting the crop on this square up here instead of moving to the dirt. Okay? So I need another move forward. I'm off by 1, right? And then I can plant 6 crops. Let's reset and run. Now I started in the right place, and I am no longer off by 1. Okay? And then puzzle, and it even says in here, puzzle completed. So with this, what I wanted to show you is what we just did. That is programming right there, right? That is programming, that is debugging, that is problem solving, that is solving a puzzle with code. That is what programming is about, right? So I really encourage you to, just come in here and practice these puzzles. They're kind of like games, if you think about it, right? They're made for kids, but you can really get a lot out of them. You can certainly get a lot out of them for sure. Okay. All right, that's what programming is about. Okay, let's move back to here. Program is a puzzle. Alrighty. We did Minecraft, so common errors, off by 1 bug, right? I didn't do that on purpose, as a matter of fact, but I just showed you off by 1 bug, the OBOB. Okay. Sometimes when you're looping, that happens a lot because you get out of the loop, or you either start early or don't do enough iterations, right? Just to show you in code real quick, last time we were seeing some code. So for example, we had a while loop and maybe a for loop, right? So maybe I'm doing a for loop, and then just for the sake of example, I'm going to plant the crop in here, right? But maybe after I get out of this loop, I need to either move forward one more time or plant one more crop, right? So that's the OBOB. So sometimes I get out of the loop and I need to plant an extra crop, right? It just depends on what the puzzle in front of you is. But this OBOB, off by one bug, is very common, right? Especially before or after loops, right? So this one, for example, while not in the file, then maybe I have a read line in file in here, right? But well, this is not a good example, but sometimes maybe I wanted to read extra characters in the file or something like that, right? So after the loop, I need to do something else, or maybe close the file, right? Close the file, right? Something like that, right? So something where the iteration is not enough and you need to do extra steps outside of the loop. That's usually what we refer to by OBOB. Another common error is the infinite loop, and we kind of got into that last time, right? So infinite loop is when you have a while loop, especially a while loop, right? A for loop will never be infinite. Well, it can be infinite, but it's harder for it to be infinite. But maybe this one was, for example, I can say in here, maybe let j equals -1. And then in here, I'm going to say j equals to j -1. Right? So it'll start as -1, and then it'll go -2, -3, -4, right? We're subtracting 1, right? And then in here, I can say while j is less than 3, right? Well, this loop is going to be infinite, right? Because j is always going to be less than 3. It'll never be greater than or equal to 3, right? Because I started at -1, or I can start at 0, for example, right? But I'm decrementing, right? So it'll go 0, -1, -2, -3, all the way up to -infinity, right? And this condition will never be false, which means I'm going to keep looping. I'm going to keep doing whatever is inside these two curly braces forever, right? That's what we call an infinite loop, right? So you got to be careful that you're conditioned to break out of the loop, right? So just to go back to the loop again. So while this is true, we're going to be executing this, but we don't want to be executing this forever, right? So in order to break out of this loop, this condition needs to be false, right? So I got to make sure, for example, to increment instead of decrement, right? And then at some point, j is going to be equal to 3 or greater than 3, in which case we're going to break out of the loop. That's what you want to do. You want to break out of the loop at some point. You don't want an infinite loop. Infinite loops are bad. That's another common bug, right? Common error in computing. All right, so last time, more software engineering comments and good names. So last time we were doing this in my first program, right? But what I didn't show you was when we said move forward, there was some code running in the background, right? And I didn't show you what this was. We just said, okay, they're kind of commands, right? And they look like this. So move forward, and then you open parentheses, you close parentheses, right? And this is our main function, which we said it's our starting point for our program, right? And it's everything is inside this curly braces, and then you have some indentation to make sure it's easier to read. So everything indented inside these curly braces means it belongs inside those curly braces, just like this one, right? These two are indented. So this is indented with respect to the main function. but this is indented with respect to the for loop, and so on and so forth. Right? So some indentation makes it easier to read. But I didn't show you what's behind the curtain on this, right? So now I'm going to show you, right? It's a bunch of functions. And so what we were actually doing with this notation was calling a function. Now in some languages, depending on the context, sometimes they're called functions, sometimes they're called procedures. In some old languages, I'm sorry, not procedures, methods. They're called methods. And then in some old languages, they're even called procedures, and they make the distinction between a function and a procedure. For our purposes, they're all the same, right? Modern languages don't really make a distinction between a function and a procedure. It's all the same. It's just you can call it a function. When you're talking about object-oriented programming languages, sometimes they're called methods, even though the key word is still function. Okay? The keyword, these are keywords. These are things that the language, the computer language that we're using to program, it means something in that computer language, right? So the function keyword means something. The for keyword means something. The let keyword means something. The while, etc., etc. Okay. So function is a keyword, and what we were doing when we were invoking, that's another word, invoking these methods, we were calling another piece of code. We're basically, what the computer does is inserts, move forward. Well, where does move forward? Oh, it comes here, and then it inserts this piece of code in there. Okay, and then we were doing an alert, which kind of triggered our browser to pop up a window that we were seeing last time, right? And if you haven't seen lecture 1, I encourage you to do it. Go see it in YouTube. Okay, it's over there. But anyways, so it's the same thing. It's very similar to our function, our main function, right? It's function move forward, and then you have some parentheses. Notice that when you invoke it, you just say move forward, and then you end your line with a semicolon, right? But notice that you don't put a semicolon in here. Okay? It's only when you're finishing like a statement or an invocation or a call, like this one. I am making a call to turn right, then I end it with a semicolon. I am making a call to move forward, I end it with a semicolon. I'm specifying a variable here, and we'll see what variables are next time, but I end it with a semicolon. But notice that when you say function, you don't end this line with a semicolon. When you say while loop, you don't end this line with a semicolon. When you say for loop, you don't end this line with a semicolon, right? So semicolon is almost like a period in the English language, right? And the reason you don't end this with a semicolon is because you haven't finished the statement yet, right? In here, in move forward, and I had this X as an example before. Let me delete this. In move forward, like, I want you to call this, and then you're done. It's almost like saying in English, move forward, and then you put a period in there, right? And when you're just writing English or any language, right? If you put a period, it's like stop. That's what the semicolon means, right? But if you just say if stop, that's like invalid, right? You haven't ended the definition of this if statement until you do all this, right? That's why there's no semicolon in here, right? That's kind of like the reasoning behind it, right? But again, at this point, don't get overwhelmed. Just flow with the notation. Okay. So going back to this line doesn't have a semicolon because it kind of needs these, right? And so in this case, the alert, yes, that's a call. I can end it with a semicolon because I'm saying just call that and I'm done with this line of code, semicolon, right? But one of the important things that we said yesterday is like, okay, we need to write programs such that not only the computer understands, but other humans understands, right? And when you get a job and maybe you go on vacation and somebody else needs to look at your code, it's very important that your code is clean that you use the right name, right? Last time we talked about, what if I just call this X? Well, that's a terrible name, right? Or what if I call it move forward, but I turn right instead, right? Well, that's terrible code, right? So you need to choose the right names for your functions and your variables, right? But also, this is a file, right? This lecture2.js. So it will help to put some comments at the beginning of this file, right? And we saw two ways to put comments: // which will ignore one line, right? So I can put some comments in here, and then on the next line, I need to put // again, right? Or another method, if you're going to do multiple lines, is you started with /*, right? And this is going to comment out everything until it finds another //, kind of the reverse. And everything in between these two things is going to be a comment, right? So I can write as many lines as I want in here, and everything is going to be commented out, right? So comments are not executed by the computer. Comments are meant for humans, right, to read and to enhance the readability of your code. So what we can say in here is this file contains the code behind movement for the character. Yeah. And then the move forward function, we can do the same thing, right? // or /start, I'm sorry, right? So we can say in here, moves the character forward 1 block, right? That's a good comment for this function. Okay, and you can see in here I already have comments for the rest of the functions, right? So basically, this is kind of you learning good habits of coding, right? Comments at the beginning of the file, comments for every function that you write, right? And this looks much better than if it didn't have any comments. Okay. Let me just check real quick if there are questions. No questions, okay. All right. So we talked about functions, we talked about comments. Sometimes you'll see this format in functions. So notice something in here. If I do / and then 2 stars and hit enter, sometimes you'll see this notation. It's the same thing, right? What matters is this right here and this, right? Again, everything in between doesn't matter if there are stars. Sometimes they keep putting stars in here. This is more for just making it a little bit prettier, so to speak, right? And so we can put this comment in here, and it'll be the exact same thing. Doesn't matter, right? So just so you know, right? You can do it this way, or you can do it. Sometimes you'll see this, right? And this kind of triggers something called JavaDoc notation, and in this case, it's not necessarily JavaDoc because it's not Java, but Java was the first one of the first languages that invented JavaDoc. But we'll get there when we get there, right? Don't worry too much about it. I just wanted you to see, if you see this, as kind of the same as this for our intents and purposes. Okay. All right. Let's continue. So we did more software engineering, good comments, good names, very important. Let's talk about decomposition. So going back to the puzzle, right? When you have a problem in front of you, you have to decompose it into smaller parts such that you can solve that smaller part, or you can solve those parts one part at a time, basically, right? So one example of this is that if somebody asks you, okay, well, simulate what you do in the morning, right? Let's write a simulation program of what you do in the morning. So tell me what you do in the morning. most people are going to say, well, I wake up, I brush my teeth, then I take a shower, then I put my clothes on, then I have breakfast, right? And it's very easy for us to think on those terms at that level, right? If somebody just asks you, what did you do this morning? You can just say, yeah, sure, I did this 1, 2, 3, and we're all good, right? But sometimes how specific you are is not the way a computer understands, so to speak, right? So again, just going back to decomposition, how would you decompose this? Well, if we just take brush teeth, right? You might decompose brush teeth, and then you can ask a dentist this, right? So, you get the toothpaste, right? And then you put the toothpaste in that step 1, just get the toothpaste, right? You cannot brush your teeth without toothpaste, or you can, but, it's not recommendable, right? So you get some toothpaste, you put the toothpaste on the toothbrush, you move the toothbrush up and down on your teeth, right? And then dentists would get really like, oh, you need to do it in circular motion for your blah blah blah, up and down, whatever, right? You can get very detailed on the instructions, but you get the point, right? We just started with, hey, there's all these steps, let's just take brush teeth, right? And let's decompose it into even smaller parts, right? That's what decomposition is, right? And what we just did here is what is called a top-down design. Okay. Now, here's what the professors at the Ivy League school would tell you. They would tell you, oh, inexperienced programmers start with bottom-up design, and then it takes them like 2 years to start thinking of top-down, and that's the way you should do it. You should always do top-down. But I kind of disagree with that. I think that sometimes you just got to do it bottom up, and sometimes it's easier to do it top down. It's just what the situation calls for, right? There's no right or wrong, okay? And that's one of the pet peeves I've got with some of these universities, and even my own alma mater, right? When I went there, you get indoctrinated to a certain point, and then you get told, oh, this is the right way of doing things, right? And then you go out and graduate and then have jobs for 20 years, and then you look back and you said, yeah, those guys weren't that right, okay? And so my word of advice, don't drink the Kool-Aid, right? It depends on the situation. But again, going back to these Ivy League professors, they'll say, oh, top-down design is the way you should do it, but it'll take you 2 years to get there. That's what they say, right? But what's important here is that you understand, top-down is you start with the bigger 30,000 feet view of, what is my problem, and then you decompose it into smaller parts. So, big problem is, what do you do in the morning? Oh, I do 1, 2, 3, right? And then you grab one of those parts and, okay, you brush your teeth. What does that mean, right? And then you decompose it even more, etc., right? That's top-down decomposition. Okay. And so with that in mind, we're going to write move backward, right? So I have in here in the code, I have move forward, turn right, turn left, and that's it, right? So if I wanted to write move backward and I already have these functions, what could I do? Right, let's think about that for a minute, right? That's our puzzle, right? That's what programming is about. Our puzzle is we need to write move forward, or I'm sorry, move backward. So let's start doing that. We go down here to the end of the kind of like what the functions, and how do we do that? Okay, well, function move backward, begin, end, right? Now what? Oh, oops, if I can spell, move backward. Okay, well, what do I do now? Okay, well, if you think about it, moving backward is I turn right 2 times, or turn left 2 times, right? So if I'm facing east, I can face south and then west if I turn right 2 times, or If I turn left 2 times, I would face west and then, north and then west, or south and west, right? So either way will work, right? So I'm just gonna say turn right 2 times. Right? And now when I do that, I'm facing the opposite direction that I was facing initially, right? Now what? Well, I can move forward, right? Move forward in the opposite direction, right? That's basically move backward is move forward in the opposite direction if you think about it, right? So I just move forward. Okay, now what? Am I done? Well, not really, because you need to move backwards like a human, though. How, you kind of like step backward, right? But in here, because you're kind of faking it, or you're kind of like turning around, moving forward. But what do you need to do again? Well, you need to turn around again to be facing the same direction where you started, right? And now we're done, right? Congratulations, we just did decomposition, right, in our heads, right? We started from the concept, okay, I understand what move backward means, but the only tools that I have in my box are these turn left and turn right and move forward, right? They're already written. So how do I do move backward, right? And we just did it, right? Turn right 2 times, we're facing in the opposite direction. We move forward 1 step, and then we turn right 2 times again, right? And these turn right could have been turn lefts. It doesn't matter, right? That is decomposition. That is solving the puzzle. Okay? And then, for completeness, we put some comments. This will effectively move the character backward 1 step. Perfect. We got the right name, we got the right comments, and we got the right code. All right. Let's move on. When should you stop decomposition? Again, decomposition is starting with a bigger problem and then start decomposing it until you have atomic functions, right? One-line methods until, so basically one suggestion would be, well, until you have a one-line method. If, in my opinion, if you have one-line method, even though I just showed you one-line methods, this is an alert, right? This is kind of bad in the sense that, I could have used this alert instead of the turn right, and it would still be one line in my original program, right? But in here, I am basically abstracting it and calling it something. If you just see alert, it's like, what does that even mean, right? But if you see a turn right or a turn left, then it means something. It's more readable, right? So that's the only time where I would say, yeah, one-line methods are okay, right? If you're abstracting it and it's clearer and it's cleaner in the code, but you're making one more call, which is more expensive to the computer, which is going to make your program slower. So, I'm on the fence on that one, right? And for now, it's okay, right? Let's just learn the concept, like, until you get it to one line of code. That's fine, right? But again, don't drink the Kool-Aid. It's more nuanced than that, and we're gonna see, how to make those calls later on. But that's, when should you stop decomposition? All right. Let's move into some more theory. And again, I told you I was going to bombard you with theory today, but it's important. Next time, we'll do a little bit more coding. We'll do more hands-on. But all of this theory is important. Again, going back to one of the things that make me sad is that, I see programmers out there and It's not that I want everybody to have a formal computer science degree, but the lack of knowledge on some of these basic things is concerning, to say the least, right? So as you can probably tell already, I don't just want you to learn how to code and then just go out there and code. I want you to have some good background, some solid background, so that you can be the best programmer you can, right? And this is for free, and then you can just go on YouTube and you can learn, and if you have questions, just ask questions on the chat, okay, or on the YouTube comments. But okay, let's get into it. So computers only understands zeros and ones. You've probably heard this before, right? It's you know, even on well, not on the Matrix, but you know what I mean, right? You've seen a bunch of TV shows. It's all zeros and ones moving across the screen and stuff like that, to represent what the computer understands. So basically, I'm no electrical engineer, but you know, it all boils down to electricity going through a transistor or not, right? No electricity is a zero. If there's electricity flowing through, it's a one, right? And then there's like billions of transistors, right? Basically, inside a computer chip, and that's what it is, right? That's what the computer does. That's what it understands. It's just all electricity flowing through or not. Believe it or not. So this is called binary, right? Zeros and ones is called binary because there's two symbols, right? Binary notation. Bi means two, right? And so we refer to that as machine language. The zeros and ones that the computer understands is called machine language. Now here's the trick. It's chip dependent. What do I mean by that? Well, you've heard of Intel chips, right? And you've heard of probably ARM chips and the new Apple chip, right? And there's like chips galore, right? And there's always been multiple chips, right? Well, the zeros and ones that Intel chips understand are not the same zeros and ones that an ARM chip understands on your phone, more than likely, right? It's not the zeros and ones that you know, the Apple chip understands. Furthermore, I would even go as far as saying, when we get into executable files, the zeros and ones in a Mac, right, are not the same as the zeros and ones in Windows, and are not the same as the zeros and ones in Android, etc., etc., right? So if you don't believe me, take a Windows executable, just grab that file, put it on a Mac, and double click on it and see if it runs, right? It will obviously not run, right? So it's sometimes, again, when it comes to executables, it's not only chip dependent, but it's also operating system dependent, right? Every operating system has its rules on how it wants those zeros and ones, right? But to kind of abstract from that, we have invented what we call high-level languages, right? And the first high-level languages, you can go back to, I think, Fortran, COBOL, and you name it, all the modern ones, right? And by modern, I mean Swift and all those. But even before that, you know, Java, C, C++, they're all high-level languages, right? Relatively modern languages. Okay. And so we don't program in zeros and ones. No one does, right? There are some people who program in assembly, which is like one level of abstraction up from the zeros and ones. And they do that when they want to be extremely, extremely fast on the chip, right? So they adapt to the zeros and ones, and they're adapting to the chip and the operating system. And they do that because they want to squeeze the last microsecond out of some execution time on that program, right? And that, again, is called assembly. But most people don't write code in assembly. Most people write code in high-level languages, right? Even if it's a super old one like Fortran. Okay. All right. So now the translation between a high-level language to machine language, to the zeros and ones, is called compilation. Compilation. And it's done by a compiler. Right? So what is that? You translate from a high-level language, C, C++, Java, C#, Swift, into Well, Swift is a bad example, and Java is also a bad example, but we'll get there. Bear with me here. Machine language is called compilation, is done by a compiler. And as a programmer, you write source code, right? So all this code that we've written, for example, this is all called source code. This is your source code. This is what we write. We call it source code. Okay. All right. So on compiled languages, here's a caveat, right? Why I said Java is a bad example, C# is a bad example, Swift and all the modern ones are a bad example, because compiled languages are kind of old languages nowadays. Well, I shouldn't say that. There are some new languages that are coming out, like Jai, that are compiled languages. Go is another example of a quote-unquote relatively modern computer language that is compiled. Okay, and so again, C, C++, they're all compiled languages. So how does it look like? Well, you write this source file, right? Like we were writing before, like, main print hello world. And then you give it to the compiler, and the compiler creates the zeros and ones. We usually call this file the object file, right? And then we already said the zeros and ones of Windows are not the same as the zeros and ones of Linux or Mac. We already said that, right? But don't worry about that for now, right? So compiler compiles your source code into zeros and ones, object file. And then usually what happens is that your code is dependent on a whole bunch of other code, whether you realize it or not. Sometimes you specifically are using what we call libraries. And libraries are nothing else than code written by someone else, right? So for example, if you're using the math library, right, you don't want to reinvent how to compute sine and cosine and absolute value and all that, right? That's already written for you in most languages. All languages have a math library, basically, right? You don't want to reinvent the wheel in that one, right? So you just use the sine and cosine that the language provides, right? But that usually lives in another file, right? And that's what we call libraries, right? So those files, sometimes you explicitly say something like import, and we'll get there. We'll see how we explicitly call libraries in some of these languages. But for now, just know that more often than not, you'll have some other files that you use it, whether you realize it or not. And the linker is what puts all of these zeros, all of these files together, and then it forms an executable file. Okay, and it's also zeros and ones. That's how compiled languages work. Compiled languages: C, C++, Go, Jai is a modern one that's still not out. It's going to be out soon, hopefully, but it's a compiled language, right? And compiled languages are fast, right? Because, well, we'll see in a minute why. But these zeros and ones are what actually execute on the chip, basically, right? There's a little bit of operating system monitoring how these zeros and ones execute, but for the most part, it's as fast as it gets, believe me. All right, so there's a difference with interpreted languages, and I have interpreted in quotes in here because some people would say, oh, Java is not interpreted, or how dare you, Python is interpreted, but Java and C# are, and blah, blah, blah. Well, this is my definition of interpreted. Most modern languages follow this convention, okay? And by modern, I don't necessarily mean better, okay? And this is what I want you to have to take with you, and what I want you to have as context, right? So again, don't drink the Kool-Aid, right? When somebody comes in and is like, oh, Python is the greatest thing since sliced bread, yeah, I'm not so sure about that, right? Or Swift is, it's the next thing, and it's modern, and it's whatever, I hate boomers or whatever. Not really, right? You again, this is it's the advent of the internet, right? Like, you just hear your own echo, and people don't have context anymore, and it's just sad. Okay, it is just sad, and it's one of the things I'm gonna keep banging on. My goal is to give you, open your eyes to the realities out there, all of them, right? And then make you choose, right? If in the end you choose an interpreted language because you think that's the best thing, then great, right? But at least you know what it is and what the pros and cons are, etc. Anyways, I digress. So, in interpreted languages, what I mean by that is something like Java, C#, Swift. Most of the modern languages follow this convention. So they do have a compiler which translate not to machine code, not to zeros and ones, but to some intermediate language. Right? In the case of Java, for example, they're called class files. It's called bytecode, I think. In the case of C#, I think it's called IL, which IL stands for intermediate language, if I'm not mistaken, or CIL or something like that, common intermediate language. Anyways, some intermediate language, right? And then you also have a linker, right, with some other files, but these aren't the zeros and ones that are going to run in the computer, right? This linker comes up with some archive, right, of zeros and ones, not that the operating system and the chip understand, but that a virtual machine understands. So what is a virtual machine? Because that's a fancy name, right? And again, I just said most modern languages, starting from Java, right, and then C# was next, and then Swift, and then all the new ones, right, have this virtual machine concept. So what is that? Well, virtual machine is nothing more than an executable file in your computer, right? And yes, it might be an executable file that is, again, going back to the assembly that I was referring to last time, like is tweaked so that it runs as fast as it can, but again, it's just another executable on your machine, right? So in Java, it's called the Java Virtual Machine, or JVM, right? And C# is some other thing, whatever, right? Your code is not running on the chip, is running by another program, is being interpreted by a program that runs on your machine, and then that program kind of runs on the chip, right, or on the on the computer hardware, right? So there's this layer of abstraction, and this layer of abstraction has a cost, has a performance cost, right? And that is why languages like Java and C# and Swift are usually, not even usually, like almost 100% of the time, they're slower than compiled languages because you have one extra interpretation step. Okay. There are some languages like Python that take this to the extreme. Python doesn't even compile anything, like it just interprets your text file, right? The Python virtual machine, so to speak, interprets your text file, like it doesn't even compile into an intermediate language. It just interprets your text file, your source code, right, and runs it. And if you remember last time, I was kind of alluding to this, like, oh, cool, we don't need semicolons, and we don't even need a main function. It just runs. It's magical, right? Well, you pay with performance, right? All that is, your text file is being interpreted. Every line is being interpreted by a program, and that is slow. The more interpretation there is at this level, the slower, right? Now, this intermediate language usually is something that is neither like a source code text file, it's very close to machine code, right? And therefore, this virtual machine interprets it, and it interprets it usually very, very fast, because it's just one step away from being true machine code. Now, in the beginning, what was the main drive to invent this virtual machine languages like Java? Well, one of the main drives was, hey, wouldn't it be cool if I just write a source file and I compile it to this intermediate language, but then I can take this intermediate language, this interpretable archive, right? I just have to only compile once. And then the same archive would run on Windows, and it would run on Linux, and it would run on Mac. the exact same zeros and ones, right? So remember what I just told you a while back, right? Like I told you, take an executable in Windows, a .exe, put it on a Mac and double click on it, or like in a Mac that you don't even double click, whatever it is that you do to run, right? It's not going to run, obviously, right? The Mac is not going to understand those zeros and ones. It's going to say, what the heck, right? However, if you take a Java program, right, a jar file, is usually this archive is a jar file, and then you run it on a Mac, it's going to run. You take a jar file, given that you have this Java virtual machine installed, right? Remember, you got to have this virtual machine installed on your computer because that's what's going to interpret it. But anyways, I was saying, take it on a Mac, same zeros and ones run on a Mac, on Linux, on Windows, on a toaster, on a phone, everywhere, right? That was the main drive with these languages, right? And that's great, right? You want to run everywhere? Run everywhere. That's great. Java is used on on everything, toasters or whatever. Like we used to, I used to see when you download the latest or whatever, maybe the banner is still there, but when you download Java and you install Java, there used to be a banner that said, Java runs on 3 billion devices worldwide. And I believe that. I think it's more now, right? Why? Because of this, right? Because it just, it's easier to compile the zeros and ones, and then you just take those zeros and ones, and then there's virtual machines for everything. There's virtual machines for the toaster and your computers and Linux and Windows and Mac and everything. That was the main drive, right? So that is an advantage. I don't want you to demonize interpreted languages, right? There was a drive, there is a purpose for them, right? But you pay with it. You pay in performance, right? So what is the opposite? So going back to compiled languages. So how do you do it such that it works on a Mac and it works on Linux? Well, if you wanted to work on Windows, you use the Windows compiler, right? You need to compile and then boom, Windows executable. If you want it to run on a Mac, you have to do the Mac compiler, right? So you compile it, and then the zeros and ones are different for the Mac, remember, right? And then you come up with a Mac executable. You want it to run on Linux, you take your source code. The source code doesn't change. Your code doesn't change. Your code is the same. But the compiler is a program that you need to download, right? And then it'll compile different zeros and ones depending on the operating system and on the machine that you're running on, right? So every time you want to create an executable for a new OS or a new chip architecture, you need to recompile. Okay. All right, we kind of spent a lot of time there, but I hope I hit the point home. Okay. All right, we're almost done with the stream here. I want to rate that nerd, so I don't want to spend too much time. But the last concept I want to talk about is this concept of object-oriented languages, right? So in the beginning, there was just things like Fortran and C and Pascal and all these old languages. They were called procedural. Now there's another realm of programming called functional programming. I won't go there, but after procedural programming, which was kind of like the mainstream programming back in the day, in the 80s, Bjorn Stroustrup, who created C++, well, some people debate it wasn't him, it was something, whatever. C++ was the most ubiquitous object-oriented language used after C, probably. But anyways, back in the 80s, Bjorn Stroustrup created C++, and in his head he had these concepts, the concept of object-oriented, right? And then after C++, Java copied the same concept, C#, Python, you name it. All of the modern programming languages, Swift, they're object-oriented languages. Another parenthesis here. When I went to college, one of the Kool-Aids that I drank, right, one of the things that they told me is object-oriented is the way to do it, right? And it's the best, not only the best way, is the way you should do it. That's what they taught me, right? They also taught me, and I'm kind of dating myself, that waterfall, and if you don't know what waterfall is, don't worry about it. We'll get to it. But they taught me that waterfall life cycle for software was the best thing, right? They told me things like, oh, you can do 9 months of documentation and 3 months of coding and you'll come up with the best code ever. Well, nowadays we know that's a fallacy. We know that is just completely wrong. Okay, completely wrong. What am I trying to get at? Don't drink the Kool-Aid, right? So don't believe object-oriented is the best way of programming and it's the only way of programming. It's a way of programming, right? And if you have a situation in which, this is just a tool in the toolbox, right? If you have a situation where this might be the best tool, then use it, right? But don't drink the Kool-Aid like I did after I graduated from college, because they taught me, it's like, this is the best way to do it. This is the way you should do it. And a lot of colleges still do that. And again, you graduate, you go work as a programmer and architect and what have you for 20 years, and you look back and you said, oh shoot, I was wrong, right? That was not, and not only, it's not that you were wrong, you have a little bit of resentment towards your professors, right? Because they told you to drink the Kool-Aid. Yeah. So anyways, I want to teach you about object-oriented languages, but again, we're going to go into it with take it with a pinch of salt. Right. So the concept behind object-oriented was, wouldn't it be cool if we could think about, going back to the decomposition, how do we think about things in the real world? Well, we think about things as a car, an airplane, a phone, a desk, a door. What are those things? Oh, they're objects, right? So wouldn't it be cool if we could somehow abstract into how our brain works? Our brain thinks in objects, right? And so wouldn't it be cool if we can start making the computer obey us by somehow following this, our way of thinking, which is in objects? And that's kind of like in a nutshell, the spirit of object-oriented, right? We can get into a lot of arguments on the details and how that got implemented, blah, blah, blah. But that was kind of like the drive behind it, right? I won't go too deep into it other than, all object-oriented languages have something called classes. A class is an encapsulation of some behavior and data. What does that mean? It means there's something that is going to be called a class. So let me go back to code. All right, so for now, class in some of these languages is going to be a reserved keyword, and then I'm going to have something like class car, right? Class car. Not character, car. All right. And this is pseudocode. This is not valid code in JavaScript, but bear with me here. And that car is going to have some, it's going to have like 4 wheels. So maybe for the sake of example, we're going to do wheel 1 is going to be a variable, and we'll see variables next time, but bear with me here. Wheel 1, and then another variable, wheel 2, and it's going to have an engine. You get the point, right? And then it's going to have methods that kind of are related to the car. So one method, for example, or method or function, right, is going to be start. You're going to start the car, right? And then we're going to do something about, right? Maybe stop, right? Maybe brake. How about just brake, right? It's going to be one function, right? And then we're going to put some code here, obviously, right? Bum, bum, bum. Obviously, we want some code here and here as well. And then we're going to do another function. You get the idea, right? Function accelerate, right? You get the idea. So all these methods or functions, along with the data, are kind of bundled into this whole thing called car. right? So the car has methods and variables, sometimes called attributes, right? And it's all bundled together into this class. That's what a class is. Right? So encapsulation of behavior and data. Behavior are the methods or the functions. Data are the variables. And we'll see more about variables next time. Furthermore, classes can have hierarchies, right? So sometimes this hierarchy is called inheritance. You inherit from your parent class some variables, for example. And I won't go too deep into this today, but just, you know, the concept that I want you to go away with is that classes have hierarchies. And then an object, right? It's object oriented. It's not called class oriented. It's called object oriented. Well, an object is an instance of a class. What does that mean, right? A lot of programmers, especially when you're beginning, have a problem distinguishing between an object and a class. And believe it or not, in some interviews, but back in the day, well, not that long ago, they will ask you, what's the difference between a class and an object, right? And some potential candidates wouldn't know the answer. Okay. So now you know a class is kind of like a template. You know, it's code, a template code, and then an object is an instance of that class. What does that mean? Well, let's go into this example. You know, I have a circle. A circle is a shape. I have a triangle. A triangle is also a shape. In this case, shape is the superclass. This is a relationship. A triangle is a shape. A circle is also a shape, right? So this arrow right here is called an is a relationship, right? And this is called a superclass, and this is called a subclass. Let's leave it at that, right? Sometimes this relationship is called inheritance. Circle inherits from shape. Triangle inherits from shape, right? And we'll go deeper into inheritance later on. But to drive my instance point home, let's say you're writing a program that draws shapes on the screen, right? Well, circle is the code that is kind of like the template on how to draw a circle on the screen, right? So how do you draw a circle on the screen? Well, it's got to be round, like perfectly round, right? It's going to have a radius, and then it's going to have a position on the screen, probably an X and Y, right? Some position on the screen, right? Etc., etc. You get the point, right? So the code that are kind of like the instructions on how to draw a circle, one circle, that's going to be the class, right? But then guess what? I want to have 10 circles on the screen. So what I'm going to do is instantiate the class 10 times. Right? Right? Did I have to write 10 times the amount of code? No, I just have to write the code once, right? The code is how to draw a triangle, a circle on the screen. That is the code, right? Just once. But I can instantiate multiple circles on the screen. I can have 100 circles on the screen, right? And each one of those 100 circles will be an instance of that class. In other words, it would be an object. At the end of the day, if I have 100 circles on the screen, I would have 100 circle objects, right? And so an object is an instance of a class, right? Each one of those 100 circles, instance of the circle class. Circle class, just the instructions on how to draw one circle on the screen. All right. Next time, we're going to see more about variables. We're going to do, hopefully we'll start doing some fun stuff, drawing on the screen, writing some code on JavaScript to draw on the screen. I know this was a lot of theory. Again, my goal is to give you a formal, good, solid education similar to Ivy League level computer science, CS 101 class to start with, and we'll go through a lot of, I I won't stop. I will just go on, right? All of this is going on YouTube and is staying on YouTube for posterity. But we'll keep on at it. Hopefully next time we'll do more hands-on, more coding. Sorry this took so long, and sorry this was a lot of theory, but it was important. All right, so thank you very much for being here. Let me just check if we have questions. I don't think we have questions. Thank you very much. We're going to rate someone, and I want to rate o.nerd. Is o.nerd here? O.nerd, come on. Yeah, he's there. All right. Thank you, guys. See you later.